Yo, what's up, everyone? Good morning. Hope you're doing well. Same old, same old. Um, and we're on our fourth week one problem set one of the year. I don't really have any more quarter four announcements. For now, just think that we're kind of doing a little bit of quarter four work before spring break, but then most of quarter four is going to be after spring break. And a lot of you might not even watch this week, and that's totally fine because it's officially the third quarter, but I want to give you a week to kind of catch up. So yeah, we're starting quarter four this week, and I think we have a pretty good lesson. I'm looking at this; it kind of looks hard to read. Hopefully, you can read it on your sheet. But we're still talking about exponents, and this lesson and the next lesson, and even the next week, week two, it's all kind of tricky. Okay, so definitely lean into that. But this is really the end of exponents, the hardest that it's going to be. Um, and what it's really all about, which maybe I should have put in the title, is you're talking about same base exponents. So really, we're just kind of learning a bunch of exponential rules, how we can kind of change exponents, simplify them, etc. And we'll just start off with something that we've seen before we kind of tackle some new stuff, which does involve solving for x again. So yeah, that's the intro. We're starting number one. It says we have 12 to the 6 divided by 12 to the 8. And what we've learned is that we can simplify anything that has the same base. Okay. And that's really what the gist of today is all about. Whenever we were solving these exponential kind of expressions before, the most important thing was that the top and the bottom base number were the exact same, right? It's 12 to the 6th and also 12 to the 8. And because we're dividing, we know that we just take the top exponent and subtract the bottom exponent. So it's going to be 12 to the 6 minus 8, or 12 to the negative 2. And again, we can only do this because they have the same base number. If we wanted to simplify this, right, we know that a negative exponent means that you actually flip it to the bottom of a fraction. So this would become 1 over 12 squared, which equals 1 over 144. So if you can simplify all the way down to the fraction, definitely do so. And just from here, you could even have known it's 1 over 12 squared, because think that the 6 12s on the top cancel out with 6 12s on the bottom, which means that there's going to be 2 12s left, right? So 2 12 squared. So that is like the division rule of exponents. And this is pretty obvious. I mean, not actually obvious because you guys aren't familiar with this stuff, but like if you're looking at number 2, we see we have 10 squared divided by 6 cubed. And we can solve this, right? We actually know 10 squared is 100. 6 cubed, we could look on the power chart as 216. So we could solve this, but we can't simplify, okay? So I'm just going to write that. And this is kind of a weird example. But we can't take the top and the bottom exponent, for example, and subtract them. We can't turn this into a single exponential, right? With a base and an exponent, right? And the issue there is that 10 and 6 are different numbers. So let me just kind of write that. This is pretty obvious. You could solve it, right? But we couldn't simplify. Good. Okay. That's number 3. Number 3 is the multiplication rule. And we see we have 7 to the negative 3 times 7 to the 5. And we know that because we have 2 7s as our base numbers, we can add their exponents the same way we would have subtracted before. So this is going to just be 7 to the negative 3 plus 5, or 7 squared, which equals 49, right? So the math is really easy, and that example maybe is even a waste of time. But that's because we have the same base number. So let's kind of just very quickly figure out what's going to be new here. For 4, we see something similar to number 2, where we have 2 exponents, but they don't have the same base. So here we have 5 to the 6 and 25 squared, right? And just like this one, you could solve this, right? This is a huge number. Like, what I mean by we can just solve this is 5 to the 6 times 25 squared. Crap. So we could solve this to 9.7 million. But what is more important is we want to figure out kind of a rule to simplify, right? So we're trying to figure out a rule. So maybe you can pause to think about how this is going to be different than this. But the key is that even though our base numbers aren't the same, they come from the same power line. That's a weird way to put it, but they can turn into the same base number if we kind of change this number. So I explained that really poorly, but let's ignore this too, right? If I'm looking at the number 25, we know that we can actually rewrite 25 as 5 to the second power, or 5 squared, right? So this number we can turn into a number with 5 as the base, right? So we don't need to change 5 to the 6th at all. But ignoring that 2, 25 is 5 squared. And if I turn 25 into 5 squared, this becomes extremely easy to simplify, just like number 3. Now, 25 was 5 squared. So 5 squared was being squared, right? And we know from our power of exponents that if we have an exponent of an exponent, we can multiply them together, right? So all I did here to simplify this was I turned my 25 squared into 5 to the 4. Think that 25 was 5 times 5. And it's just 5 times 5 times 5 times 5. So there's 4 5s here. So hopefully you think that's really cool. And that's going to be the basis for the rest of this. You have to be able to recognize if numbers have a base number in common. 10 and 6, like you can divide by 2, but that's not what we're talking about. We're talking about numbers that are squared, cubed to the 4th. They all can be rooted back to the same base. So 6 and 10, you can simplify, but 5 and 25 share that common base number of 5. So yeah, that's that. That's the first really important part of this. 5 to the 6 times 5 to the 4. We can simplify to 5 to the 10. And it's going to be the exact same thing that we solved to before, right? So again, you want to simplify if you can. That's the whole point, okay? So yeah, you could have solved this the whole time, but we just learned a really powerful rule of exponents. Sorry, my hands are always like so wet and make the paper look crappy. So that is really the rule. And for the rest of this, we're going to kind of talk about it and how to use it. So here we see 36 squared divided by 6 cubed. And this and this are the same pretty much, with just multiplying versus division. What I want you to start noticing is if you ever see these exponential expressions, look to think, can your base numbers have this become the same? I said that poorly, but yeah, you see what I'm saying, right? 36 is 6 squared. So I can rewrite 36. I'm taking 36 and turning it in to 6 squared. Okay, that's the key to this lesson. Take the number that's not the same base number and turn it into the same base. This is kind of the exact same as the last one, and maybe I should have changed like the concept, like the numbers a bit, because it turns into 6 squared. So this becomes 6 to the 4 divided by 6 cubed. So there's 4 6s on the top and 3 6s on the bottom. So this is just going to become a 6. Hopefully that makes sense. Okay. Both multiplying and division. Try to make the base numbers the same. Now we're going to go back to solving equations. Okay. And the next lesson is going to be challenging. And that's okay because it's good to challenge everyone. I like to challenge you. Um, but I don't want you to worry about this being a super, super important topic. Okay. It's challenging, but I think in a pretty satisfying way as well. Anyway, that's a lot of crap I just said. Okay. So if we're looking at number 6, it says 4 to the x is equal to 64. And what's new now is that we're going to be solving for x again. Okay. We've just been simplifying, right? We haven't even been looking at equations. Even when we were looking at variables, like, something that we've been looking at is something like x squared times x cubed, turning that into x5. We've been doing that, but that's not an equation because we're not solving for anything, right? Once we put an equal sign into it, things can be a little bit more complicated. So here, know that for the next 3, our goal is to solve for x. We want to figure out what is x in this equation. So we're going to have to kind of think about this from a slightly different lens. We have 4 to the x is equal to 64. We have to think 4 raised to what power gives me 64. Okay, that's the first way to think about it. And some of you might already be able to solve that. However, what's even cooler is let's kind of try to apply that same base concept, right? So here, what you should notice or think about is that 4 and 64 have the same base, right? We can reduce 64 to 4 times 4 times 4, right? 4 to the third power equals 64. So even if I have an exponential equation, my goal can be to turn my base numbers into the same thing. So I don't know how perfectly I explain that, but 4 to the x has 4 as a base. Let's turn 64 into 4 to some power, right? And I gave you that power chart before, which is useful, but you could try 4 times 4, doesn't work, times 4. And you'll see that 4 to the third power is the same thing as 64, right? So this and this are equivalent. And this, I'm hoping isn't too confusing because it's actually obvious, like once you like kind of see what's happening. All we just figured out was that 4 to the third power equals 64. So x obviously equals 3, right? Hopefully that makes sense. If we're looking at the original equation, 4 to the third power equals 64. But once the equations get more complicated, this was fairly easy to solve. All you're going to start doing is once you have the same base, you can just ignore the base, okay? So 4 to the x equals 4 to the third. So obviously, x equals 3. I hope that makes sense to everyone. So that's the start. And let's already kind of challenge it a bit and get a tougher question with number 7. And I think this one will be good to help us understand the concept. It looks awful, right? This is not a pleasant thing to look at. We have 4 to the x times 2 to the 5 times 32 to the negative 2 is equal to 2 to the third. And we want to solve this, okay? Our goal is to solve for x. And while this looks awful, what you have to realize is that it's just a longer version of something like this, where all we really have to do is turn every number into the same base, okay? And in this case, the base number is going to be 2, right? It's usually not going to be too hard to figure out what the base number is, but you can always test. But if you can kind of realize or remember that 2 to the 5 is 32, all of these can be turned to 2 to some power, right? So if you're ever trying to solve an exponential, the first thing you do is turn them all to the same base. Let's start with 4 to the x. We ignore the x, right? And I don't know if I'm saying all this perfectly, but hopefully you can see. What is 4 in relation to 2? It's 2 squared. So we have 2 squared to the x. That's our first one. The second one already was 2 to the 5th power, right? So we had the right correct base number. 32 is 2 to the 5, as we were kind of seeing before. And 2 to the 5 is being raised to the -2 power. And then finally, we had the correct base here. So if I've been saying it poorly, hopefully you can visualize now. All you're trying to do is make everything a 2. Now we see that we have 2 times x, okay? Because you multiply together an exponent of an exponent. So we have 2 to the 2x times 2 to the 5 times 5 times -2 is going to be 2 to the -10. And then on the other side, we have 2 to the 3. This is a hard question. Like, I think I definitely went 0 to 100 real quick, and that's okay. Our next step is once you have the same base, you can just add them up, right? So if I ignored this and I was just looking at this, it's the same thing as we were seeing over here. We can add up the top numbers. So even though we have some x's and some numbers, and that's what I think is going to get tricky, all we have to do is add up the exponents, right? The whole point of putting them all as the same base number is that once they have the same base, we can take all of their exponents and add them up, right? So it becomes 2x plus 5 minus 10, which is the same thing as 2 to the 2x minus 5. And once we get it to this step, we're in a really, really good place because there's only one base number on each side, right? So that's what's really powerful here. Once we've turned the equation into the same base number, we can ignore the base and then kind of solve the tops. So here we have 2x minus 5 is equal to 3. Hopefully that's okay. I know that this has been kind of confusing. I'm seeing that now. But again, you take something like this, I kind of just wanted to make it as challenging as possible. Well, not as challenging as possible, but like as challenging as reasonable for you to understand. You're taking everything, turning to the same base, adding up your exponents, and you do all of that just so that you can have a linear equation at the very end. So I'm doing this quickly, but we're isolating x, trying to get x by itself. So I move over 5, and then I divide by 2. Okay, so yeah, I'm not going to do number 8, and I'm going to make sure that your practice questions are more like 6 with some challenge like 7. If the end was confusing, that's totally fine, and we'll make sure to review more next lesson. Alrighty, proud of you.